I'm also a part of the Robert Bosch Center for Data Science and AI and the American Express Lab for Data Analytics, Risk and Technology. So I encourage you to kind of Google up about it, find out about it, see how you can be a part of it as well. So unfortunately, I've not actively taught in online BSc so far. I hope that changes sometime soon. So you might not have, unlike the other people in the other rooms, you might not have had a course by me, but hopefully the future batches that will change. So today I wanted to talk about experimentation and machine learning. I actually debated that preposition. I wasn't too sure if it should be to, in, or use a conjunction like and. But basically, I wanted to connect these two. As I'm given to understand, many of you are midway through your program, right? So some of you are in the early stages, some of you are in the slightly later stages. But ultimately, many of you have gone through some basic set of courses. And I wanted to try and connect it with this core tenet of experimentation. Now, a lot of times when people use the word experimentation, I guess your brain goes back to high school, right? This chemistry experiment, biology experiment, right, that we did. We're going to talk a little different. We're going to talk about a slightly different kind of experiment. And you'll see that soon. What is this idea of experimenting when it comes to data and when it comes to machine learning? Okay. So broadly, I'm going to try and give a motivation. Okay. And the motivation is, see, I want you to start thinking of experiments as a way of controlling your data. Right? And in a second, I'll explain how experiments are a means to control the data, as opposed to what you are used to right now through your traditional analysis where you're given a data set. This is an online BSc in data science, right? Programming in data science. Almost anywhere you go to, when you try to explain with someone data science, right? Let's say you go and try to explain this to a high school student or your friend or something. Your approach will usually start with, okay, so imagine there is this data. And then blah, blah, blah. You do all these cool things and you save the day, right? But you start with data, right? But what if you don't start with data? What if you have a problem? You've not even thought about the data yet, okay? And we're going to try and tackle that. So ultimately, I'm going to talk about experimentation. Pretty soon, I'm going to start a little later in the lecture using a word called active learning, which goes into the machine learning paradigm. In all of this, the core tenet that I'm going to talk about are ways in which you control the data, rather than everything you have been used to, which is somebody came and dumped this data onto you, and then you did the analysis. Okay? So we're going to start with saying, hey, if you have to control the data, is that a challenge or is that an opportunity? So you're already thinking, I'm spending all this time, I'm studying for this program, right? It has become clear to me that analyzing data is not so straightforward. Coming up with predictions from data, not so straightforward. Otherwise, why are people paying data scientists the big bucks? Otherwise, why are we having all these degree programs? So analyzing the data is a challenge, but now on top of it, you want me to control the data that goes in, which gets analyzed. So is it really a challenge or is it an opportunity? We're going to talk a little bit about that. And then I'm going to start from a little bit, just in a very similar way to how every machine learning course starts with a regression, right? Just to get a feel, how many of you have heard the word regression so far? So good, right? Guys, regression existed way before. I won't even say computers existed, way before even the concept of computer science existed, right? So regression comes from way back. Similarly, before we get to some advanced topics like active learning, we're going to talk about experiments. We're going to talk about something called design of experiments, right? And then finally, I'll end with online learning, which is a kind of another new paradigm in learning. Okay? Midway through this, feel free to raise your hands. If you have any questions, comments, you can share it with me. I'll integrate it with the lecture. You don't have to feel like it's a one-way street. I know it's a big class, but that's fine. Yeah. Yeah, so I'll repeat the question. So many times we analyze data. So you take an example. So everything that you've learned, I'm assuming so far, I'm assuming you've not had a course in design of experiments, right? Um, so I think if it's not a fair assumption, do let me know. But broadly, our problem statement is start with data, analyze data, either get some insights from data, like recognizing patterns like clustering, association rule mining, or make predictions on the data, right? The supervised learning paradigm allows us to make predictions on the data and use it for, business or for research or whatever. But imagine in this example, for instance, someone says, hey, there is this data of the stock market, you want to analyze it, but what happens if someone starts controlling the data? The idea is, well, first of all, you're not in charge of who's controlling the data. You get the data as it is. But what I'm going to point out to you soon is, if all you do in many situations, if all you do is consume the data passively, you come to the realization that you're not able to make the kind of conclusions you want to. You're not able to make good predictions. So if you have the opportunity to control the data, I'm going to motivate why you need to take that opportunity. Okay. In many situations, you don't have that opportunity. In the most famous example of this is smoking and cancer. And unfortunately, it's sad to say that one of the most famous statisticians was so wrong about it, Ronald A. Fisher, who till his deathbed kind of insisted that smoking does not cause cancer. But the most interesting thing about it is you have some data about smokers and you have some data about cancer. Your only option is to analyze it. You know what Ronald Fisher would have loved to have done? He would have loved to have given cigarettes to people and made them smoke, and not given cigarettes to some people and forced them to stop and then seen what happened. Right? Because that's how an experimenter thinks. Pretty soon, I'm going to talk to you for the next half an hour, 45 minutes about why that's an awesome approach. Where if you can control things, you have much more clarity on the data and why your results from the same analysis of the data will be much better. But unfortunately, there are ethical constraints, there are real life constraints, there are engineering constraints, there are legal constraints, where in some situations you can't go play with people's lives and so on. So of course, take all of this with a pinch of salt, but I'm going to give you some concrete examples of at least how knowing that the data you're receiving is not curated by you, but happens naturally, itself makes you a little more cautious of it. Let me start with the story of another famous statistician who was at that point, this was during World War II, okay, and he was in Columbia University at a research lab, I think statistical research group or something in Columbia University in New York. And it goes directly into what we're talking about, okay? I'm so glad someone asked this question, and I just gave the example of Ronald A. Fisher and cancer because this appeals to that. So he's analyzing the data, and what they analyzed was, where do planes get hit by bullets? So the planes were flying in certain patterns, and they were getting shot at also by people from the ground, by other planes. And so what they decided to do is, so they need to kind of make the planes a little stronger, right? If you want to make a plane stronger, you want to put a sheet of some protective metal on the outside. The key question they wanted to ask was, are the bullets hitting the plane completely randomly, or are they more likely to hit certain locations? Now, this is a hard question to answer in principle, right? Because it's not as much an aerodynamics question. It's not as much a pure geometry. It has to do with how the fighters are flying also. It might be that they get hit only when they're kind of doing the nose dives, or are they getting hit near hills and not valleys? Mess. So they said, let's go to the data scientist. So as a data scientist, what do you think they did? Guesses, yeah.
I mean, they randomly took the samples of the planes which crash landed and saw where the bullet marks are.
So what they did is a good start. So what they did, and I won't give away the full suspense in a sense. So what they did is they took planes and they took planes and they analyzed the bodies of the planes where the bullet holes were. So they took a corpus of, I don't know, a large number of planes that had come back, and they looked carefully for where the bullet holes were. And based off of that, they came to a couple of conclusions. They said, look, first of all, it does not look random at all, where the bullet holes seem to be coming in. They seem to be hitting far more of locations A, B, C. I'm not going into the technical details because I don't know them, but they used complicated words like fuselage and things like that. But I mean, if you're an aeroastro person, it might be of interest to you to read up on the story. But what happened was their conclusions were that planes are primarily not getting hit in locations A, B, C. The problem with this conclusion, and Wald was the first person to come back with this, was that the sample of planes on which they were able to look at bullet marks were ones that were easily retrievable or ones that came back. It turned out that by doing the kind of analysis they were doing the opposite of what is good, because the planes that were getting hit and the ones that were getting hit at the most vulnerable parts were not even making it back. Right? This is the kind of story that motivates people in experimentation. Sure, you can't put a plane up there and decide to shoot it. But at the very least, we need to realize that when we do data analysis or data science on many, many, many problems, you're not looking at a balanced data set. You're not looking at an experimental data set that came about from you conducting an experiment. This is what we call as observational data. You observed the bullet holes on planes that made it back, but without the realization that these are the planes that made it back successfully. Imagine the bullet holes on the planes that did not make it back. You never saw the data. So imagine all you're doing is you've got this entire spreadsheet and you've got all of these data points on where planes are getting hit. But what are the conclusions you're drawing? They're the exact opposite ones. You might be concluding that, hey, planes are not getting hit on the engines. But in reality, planes are getting hit on the engines. You're just not seeing it because those planes are not coming back. I'm going to give you a couple more examples. Some of these are very common ones. Some of these are popular. How many of you know the ice cream and heat strokes story? In any of your classes, has that come up? Because that's a little bit of a popular one. So the way ice cream and heat strokes goes is this. It turns out that if you do a basic regression analysis on a variety of input features related to days when heat strokes are highest, one of the variables that's most highly correlated is, guess what? Ice cream sales. So days where the most heat strokes happen are the days when most ice creams have been sold. Right? So as soon as someone sees this, what is the conclusion they're going to make? But they make an even worse conclusion, right? Which is ice creams cause heat strokes. Right? At least if they said that, on these days this happens, that's okay. But is this hard to believe that the data would have told you this story? Would you believe that? Could the data have said this? Or did someone mess with the data? I don't know. I would believe this because what do you think is going on? So I'm going to repeat what she said loudly, because on days that are very hot, more people go for ice creams. you might even say, okay, but suppose I were to do, so first of all, if you were to do a regression analysis, a very good chance that the most significant variable would have been ice cream sales of the day. Here, each row is the number of heat strokes on that day in a particular county. And that's the output variable, and the input would have been the bunch of things. And you might even argue saying, well, but if I had put temperature as one of the inputs, well, all of you know how regression works, right? Sometimes these variables compete with each other. One can explain away the other's importance. You might have heard a very complicated word called multicollinearity at some point, okay? So don't worry, multicollinearity is just a very fancy word for the fact that there is a correlation between the columns of your input variables. So if temperature and ice cream sales are correlated with each other, first of all, the confidence intervals on each of these variables will be very wide, if that's something you remember from your classes. But it's also a fundamental problem. You really don't know. I happen to know that ice creams don't biologically influence heat strokes. As a medical expert, I need to know that. But there are many problems where I don't have a medical expert. If all I had was the data, ice cream sales looks as good as temperature in terms of being an indicator for heat strokes. In fact, it might look even better than temperature. Why? Because there is something about a heat stroke which requires it to be hot and dry. So maybe you want ice creams on such days. So temperature alone might not be good enough. Humidity alone might not be good enough. But ice cream sales is very good. It's the best proxy indicator for heat strokes, even better than maybe the variables that are causing it, right? So I've given you two examples. I'll give you one more example as a joke. Okay, so yeah. So logical biases. No, what I'm explaining is that data science, take that word science with a pinch of salt. What I'm saying is that, see, you need to carefully think about the source of the data as well. And I'm going to motivate how there are certain areas where we can control the way the data comes in, or at least being aware of the fact that the data itself could be observational data might mean that you can't say things like A is causing B, right? Or you might have to say that we need to go look for data in certain locations. Or if you have control over which data to create, you create the data in specific ways. We're going to talk about some of those approaches. Anyway, let me just quickly motivate it with two more examples. Training programs and degrees. Often you keep coming across this question, right? IIT Madras students. If you look at IITM students versus students in other colleges, you might see that any achievement benchmark, let us say GRE scores, GMAT scores, admits into IIMs, all of these, IIT students are doing much better, right? Now, is that because of IITM? Is that because of the learning that the teachers impart on the students? Why do you think this is the case? The screening, right? The screening itself allows only, so it's the people who come to IITM are not a random sample. If I take the country and take a random sample and put it into IITM, take a random sample and put it elsewhere, and then say, hey, look, these two look different, that would be a completely different story. Now, I'm not saying we should change the admission procedure of IITMs. That would be like a lottery system, right? What I am saying is, first, as citizens of this world, not even just country or state or something, as citizens of this world, first let us be cognizant of this. So we stop making erroneous conclusions or conclusions that are not validated, right? So a simple conclusion is, oh, IIT is making these guys very smart, right? I hope that's true. We work hard towards that. But it does not logically only follow from the data unless you do something substantially more complicated. You can't just look at the data blindly and just say the outcome is X number of startups from IIT, X number. Doesn't make sense. I mean, sure, that might be a true statement, but you don't know how much IIT or its faculty have contributed to the same. Mm-hmm. Yeah. It's still a challenge. It's still a very interesting challenge because you still do represent a part of the population that took initiative to sign up for a program. If I compared you to people who didn't sign up for this program, you could kind of say, hey, I'm doing much better. But where is the problem? The problem is you probably already wanted to move up. Probably already wanted, thank you so much. You probably already wanted to do better. So this is a standard thing in many training programs or degrees. You really don't know if it's as long as people are choosing to get into something. Now, something interesting happens. Sometimes something called a natural experiment happens, right? So let's think about, and by the way, natural experiments is what won the Nobel Prize for the economics the last time around. Okay, so natural experiments are these really cool things. So imagine that for the 10,000 seat, about 12,000 people applied. And so now we do use a lottery system. Right? If we do that, imagine people who sometimes get admitted but are not able to come because of some temporary emergencies. Right? I mean, how would someone on ice cream and heat strokes wanted to have done it? Ideally, they would have said, if I really need to see if ice creams cause heat strokes, I need to look at days that are, so right now I'm looking at days where ice cream sales are high. But days when ice cream sales are high also happen to be the hottest days. Now, I also see data on the other side. I see days when ice cream sales are low, but they also tend to be the cold days. So, suppose somebody came to you and said, I can give you more data points. And you say, thank you. I always like more data as a data scientist. And they come and say, hey, I've got a data point for a hot day when ice cream sales are high. Do you want to know how many heat strokes? I already have a lot of data like that. I already have a lot of data of hot days where ice cream sales were high. I already have lots of data like that. And what have I seen historically? That heat strokes were high on those days. Similarly, a person comes to you and says, hey, I can give you another 10 data points. I've collected it, or I can go and collect it on these 10 days when ice cream sales were really low and the temperature was also low. Can I go check with the hospital as to how many heat strokes were there? No, that's not going to help me anymore. What kind of data points do you want? A little louder. You want data points where the ice cream sales were low, but the ambient temperature was high. Unfortunately, you don't have that. But if you could collect it, you'd want that. Similarly, I'd want days when the temperature was low, but ice cream sales were high. I'm basically specifying the inputs for which I need the output. Now, I can't get that. But one is a complement, but that's still a very useful data point, nevertheless. But the most important thing is sometimes natural experiments help you. Okay? Natural experiments are ones where, imagine a day when it was really hot, but there was an ice cream workers' strike. Completely random. It just happens. Right? So, economists carefully dig. So there was about 4 or 5 years ago, I'm not too sure actually how many years ago, Abhijit Banerjee and Esther Duflo won the Nobel Prize in Economics, and that was for randomized control trials, a form of experimentation, right? Actual experiments. But sometimes when you can't do actual experiments, you can do that. There are natural experiments that give you a kind of insight on what is going on. So we very carefully kind of scour for that. The last one that I wanted to talk about is promotions and discount. Again, here is another problem where you really can't tell what's going on. Normally, when there is you're the owner of a showroom or a supermarket or some business establishment, and you want to see the effect of promotions. So you've got you've got like monthly sales or daily sales, and you want to do a promotion. But often these promotions are linked with an offer. So it's not just the advertisement. So suppose I say, hey, I want to give a 5% off. But every time I give a 5% off, I advertise 5% off. How do I know whether it's the 5% off that is getting people into my store or the fact that I'm shouting it in middle of the IPL matches continuously? Which one is contributing to my bottom line, right? I don't know. So this leads to this annoying problem of correlation is not causation. The reason people come in and say, and for a data scientist, that's so annoying, right? Because you want to say A is causing B, because that's when you're useful. You're saying A is correlated to B, okay. Ice cream sales are correlated to heat strokes. What do you want me to do about that, right? But if I say A is causing B, now I know what to do. I can go and say, don't have ice creams. It causes heat strokes, which is not true, by the way. I'm just saying it as this thing. So we want to break through this. Okay, we want to break through this. We want to break through this problem called multicollinearity, which is a fancy word for correlation. So whenever you're dealing with data, keep in mind that one of the biggest challenges you're facing is the fact that columns are correlated, and that's not a good thing. That's not a good thing from a statistical perspective. As you would have learned in regression, you would have learned another fancy word called variance inflation factor, or you might have learned that you have to do a statistical test for each independent variable, and that will fail. All of these problems are mathematical consequences of a core logical problem, which is if two variables are correlated, how the hell will I know which one is causing my output to change? If I keep doing promotions only when I give discounts, there is no logical way, leave mathematical way. There's no logical way for me to know which one is causing the increase in sales. Unless, of course, I use science, I use marketing, I use biology, I use legal, I use engineering. But those are not data science paradigms, right? Okay. So this also highlights that not all data points are worth the same, especially when we come to active learning in a few minutes. I'm going to talk about approaches which are targeted towards finding that data point which is most useful. We saw in that ice cream sales, we don't want data points where the temperature is high and the ice cream sales were high. What do I mean by we don't want the data point? I don't need to know how many heat strokes occurred in situations like that. I don't need that output for this input. This data point is not useful. If you, however, give me data points, that is, you tell me how many heat strokes happened on days which were cold but many ice creams were had, or you give me data points, and how could that happen? Maybe the ice cream shop gave a discount, right? Or you give me data points for days when the temperature was high, but ice cream sales were low. I'll immediately be able to reject the notion that ice creams have anything to do with heat strokes and that it is primarily temperatures that are driving heat stroke. I'm going to use the same method, by the way. Same good old regression, same good old K nearest neighbors if you've heard it. Any of these other techniques that you've learned. Same methods of analysis. But what is different? The input that came in is different. The data is different. Okay. So having said that, poor girl, she thought I was chasing her when she was going. Okay. So let's talk a little bit about how designed experiments work and how they tackle this problem. Okay. Yeah. Yeah. Mm-hmm. Yeah. So the gentleman was saying that, hey, you started off by saying that you start with the data. Is that really true? Don't we kind of do a context setting and don't we kind of design an experiment and so on? So, well, the answer is it depends. In many situations, sorry? No, no, back. I don't want this slide. I won't. Huh? Can I keep it on this slide? Is that okay? That, no problem. Okay. So the answer is, well, in many situations you can't conduct an experiment. So it's not true that a typical data science problem involves experiments. Most data science problems. Sure. So it is true that many data science problems starts with data collection, but I want to differentiate between data collection and experiments. So what's the difference in data collection? You might do a lot of work. So sometimes people come and hand you some data. That's the easiest. Sometimes you have to go get the data. All that you're saying, which is identifying the objective of the study, context setting, all of that is fair game. Okay? But in some situations, you're not given the data, you have to go gather the data. Okay? But gathering data is not conducting an experiment. What is the difference, do you think, between gathering data or collecting data and conducting an experiment? You know, honestly, even an experiment need not start. I mean, most experiments do start with a hypothesis, but I wouldn't say you kind of prove a hypothesis, right? You try to falsify a hypothesis. So, in a sense, even though you have a hypothesis in place, there's a difference between using the word hypothesis to mean agenda versus hypothesis in the scientific sense. A hypothesis in the scientific sense is truly to say you're just formulating the hypothesis to falsify, right? So in both cases, you could have a hypothesis in your mind. So I wouldn't say that's the key difference. Yeah. No, but the data might not. Imagine you buy a new sensor. So imagine there are people going through a traffic light and nobody knows how many, but then you put a sensor. So for the first time, the data is getting created, right? So I wouldn't say it's even that. There's just one person. Okay, so controlled conditions. So that's one difference. Formal experimentation is different from just data collection in that you make systematic and purposeful changes to the input variables. You control which inputs get in. So you're all used to this, or there's no whiteboard, but you're all used to this X matrix, right? And Y vector. Guys, everything in your classes must have been one X matrix and one Y vector, correct? And you're trying to get an f of X in between. The rows of the X, if you decide what it is, you don't decide what the Y is, then that's just cheating. That's making up your own data, right? That's nonsense, right? I can make up my own data, make up my own analysis. But there is nothing wrong what an experiment ultimately is the control of that X matrix. You're carefully curating what that X matrix is and then interacting with the environment to get Y values for each of these X's. When you put in a sensor or when you go carefully collect data, you are populating the X and Y, but do you have control over what values show up in X? An experiment controls what values you're willing to put into X, with absolutely no control over what happens in Y, because it has to happen. You can, at the most, kind of say, I'm going to carefully send out a promotion without giving a discount. What have you done? You carefully set in that X matrix under the column called promotion, put a 1, under the column called discount, put a 0. But how many people bought the product? I don't control. That's a Y, that is a natural consequence. That is data that I get from the world. Right? So an experiment is different from data collection in that it involves systematic and purposeful changes to the input variables in an attempt to gain knowledge about the system or find the ideal settings that result in the best output. This, I really like this only because I've eventually kind of come up with this over time. I didn't copy paste it from somewhere, so that's the reason I kind of like it. But I've thought through it, right? It involves systematic and purposeful changes to the inputs. You decide what is in the X matrix, and you go get the values for Y. When you decide what's in the X matrix, you can make sure that the columns don't have correlation. And that's beautiful because it allows you to not only do an analysis and understand which variables influence the output, but it also allows you to do something really powerful. It allows you to say A caused B, not that A was correlated to B. What about an experiment allows you to say something as bold as A caused B? It's the fact that experiments follow certain tenets, and I'm going to talk about those tenets. First of all, we make sure that our features of interest are uncorrelated. The fancy word for that we use in statistics is that they're orthogonal. In the design of experiments community, you don't use the word features, you use the word factors. So I'm just, in case you pick up a textbook, you might get confused. Factors are orthogonal to each other, okay? But that doesn't change the fact that, so take the case where you were dealing perhaps with promotions and discounts. That is two factors, right? And you make sure that they're uncorrelated, then great. You can study the influence on the sales and you know how much a discount helps and how much a promotion helps. However, there are other things like noise, right? Things that you never intended to study. Imagine someone came to you and said, ice creams cause heat strokes. The mic is back? Okay. So I won't shout that much. Okay. So let us say this ice cream had caused heat strokes. Now it's because you know biology that you think temperature might be involved, right? You know medicine in that sense, right? If you didn't know that, medicine might not have been a factor to begin with. It's a noise variable. Promotions and discounts are things that you have control over. Maybe ice cream sales you have control over, but do you control the temperature? You don't. So there are many problems where there is noise in the system. There are many things you've not thought of which are correlated. The example that hostel students usually, I'll just mention this example because IITM hostel students love this example, is which breakfast item is the most popular? Okay? A breakfast item which is the most popular can be measured by the number of people who show up, right? Now you have control over which breakfast item is given. However, if one item is given on a particular day of the week and another is given on another day, how do we know whether it's the day or the item? So for instance, puris are always given on Saturdays. How do I know if the people are coming for the puris or because it's a Saturday? So what we're going to do is we're going to try and do three things. One is, first tenet of experimenting is sometimes you like to control things. By the way, between Puri's breakfast items, promotions and discounts, what were the other examples I gave in the previous slide? Online degree programs. Which one do you guys like the most? I'll stick to that and explain these three concepts. Puris. Okay. This is after lunch, but still continues to be the most popular topic. Okay. This is the following problem. The problem is puris are always given in Saturdays. What's a competing thing for puris? Breakfast item it has to be. You can't say butter chicken or something like that. Or you can, maybe you like that for breakfast, but huh? Hey, that's so close to puris, man. Come on. Dosa. Okay. The slight this thing. Okay. So puris are always given on Saturdays. Dosas are always given. Okay. I'll go with this example. I'm going to change the example when I come down a little bit because I want to bring in another concept. But okay, for now, dosas are given on Wednesdays. Puris are given on Saturdays. We're measuring footfalls. Footfalls is a measure of number of people who come into a particular facility. Supermarkets love to talk about it. Physical stores love to talk about it. Even online stores have some notion of number of visitors. Okay? So we're doing this, and so we do an analysis. The 101 data scientist who has taken the online BC but not sat in this room today, what will they do? They will analyze the observational data that came up and perhaps conclude that puris are the most popular. My fear is that puris are anyway going to beat dosas. Let's flip it. Okay. I don't know. Don't you guys think puris are generally going to beat dosas? Yeah. So okay, puris are on Wednesday, dosas are on Saturday. Everybody happy with that? Okay. So no more changes. Dosa is on Saturdays, puri is on Wednesdays. Okay. And the data scientists who didn't sit in this room today, what are they going to do? They're like, I have taken online BSc degree. Let me go analyze the data. And they're going to report to upper management, the hospital administration, not much of upper management, but still, the administration at IITM saying that dosas are 25% more popular than puris. I've analyzed the data. I'm a smart person. I've taken the online BSc course. Okay? So don't mess with me. So anyway, so the hospital administration, he's taken online BSc course anyway. So clearly, more rewards for the chef who cooks the dosas, double the contract money, dosas every day. Okay, problems with that. However, you guys, you're all smart. Okay, so you take on three approaches. You understand that observational data is not experimental data. And here is an example. First of all, if I can control something, I should control it. Two, even if I can't control it, at least I should be cognizant of this fact that the problem could have been Wednesday and Saturday. Right? Wednesday, 8 a.m. in the morning, there are classes for students. Many of them skip breakfast because they need to rush to class. And they've been up late the previous night. So what we can do is we try to do three things. One is called controlling. Controlling is this idea that I'm going to conduct an experiment where I'm going to fix the day. So I'll fix the day as Wednesday, right? And on half the Wednesdays, I'll give dosas, and half the Wednesdays, I'll give puris. That way, I'll know the true difference between dosas and puris. Approach one, okay? Now, I'm going to skip blocking and I'm going to come back to this, but I'm going to come to randomizing in a second, okay? So randomizing says, well, you thought very carefully about Wednesdays and Saturdays. But did you think about other factors that could be there? Such as the fact that as we go closer and closer into summer vacation, people's appetites go down. I'm making up stuff, okay? But still, people's appetites go down, and there's a small trend that with the hotter months. So in your experiments where you said the first 4 Wednesdays I'm going to give dosas, and the next 4 Wednesdays you're going to give puris, it's not a fair fight because people in general eat more in March than in April. or half the students because of COVID wave 2 went back home, or something else happened. So what we need to do is we need to randomize. How do you randomize? What you have not controlled. So you have control that it's all on Wednesdays. Between those 8 Wednesdays, randomly allocate some Wednesdays to puris, randomly allocate some Wednesdays to dosais. Control whatever you can, block whatever you can, but randomize the things that you have not even thought of. Now when you randomize, even if you have forgotten another variable, like month, like whether it was the first Wednesday of the month, or whether something special was happening, there is no systematic bias. Okay? Now sometimes you don't want to control, you want to block. Blocking says, see, okay, you did it all on Wednesdays. But there is a small thing. Puri is an indulgence food. It's a food that is best enjoyed when there is lots of time. I'm again making things up. Okay? But imagine that there was a particular dish that takes time to eat, but lots of people like to eat it. It's a hit on Saturdays. By forcing everything on Wednesdays, I'm not capturing that nuance. See, I do want to tell that which breakfast dish is better. But you can't force me to analyze that only on Wednesdays. What if there is a relationship between the day, and the food item? Some items are easy to grab on the go and eat while you're walking. Some items require you to sit and eat. Blocking says don't control. Blocking says instead of controlling it all to Wednesday, split it across Wednesdays and Saturdays. Half the Wednesdays puris, half the Saturdays puris. Half the Wednesdays, the remaining half Wednesdays dosais, remaining half Saturdays dosais. So you not only have made it balanced, but you've also observed any interaction effect that dosais and puris might have with Wednesdays and Saturdays. Right? So the 3 tenets that experimentation follows is: 1, some things you try to control by keeping constant. Some things you try to block by making it balanced. The other things you randomize. So often, colloquially, there's one mantra which says block what you can, randomize what you cannot in experimentation. But because you do this, I can now say that whatever observations I'm finding is not just the correlation. I can say things like puris cause more people to come in, because I've blocked for the effect that it could be a Wednesday or Saturday. I've controlled for the effect that it could be a Wednesday or a Saturday. In the past, if I was analyzing data, I could only say that I am observing a high correlation between days when puris are given and people are coming. In fact, in our case, we would have said the opposite statement. We would have said, I'm finding a high correlation between days when dosais are given and people are coming, because I didn't even realize that it was the Saturdays that were making people come, not the dosais. Right? Okay. Any questions on this at this stage? Yeah. So let me answer that question and get money. So how do you know that any factor that you're blocking out is successfully implemented? See, if you pick a factor, so for instance, if day is a factor, day has 2 levels. In this case, Wednesday and Saturday. Although it could have Monday, Tuesday, but in this case, it's Wednesday and Saturday. What you make sure is that on equal number of days, that factor called Monday is given and the factor called Wednesday is given. You make sure that the correlation between the column called day and the column called food type is 0. So you have a mathematical definition of what complete blocking is. So that's why you kind of block what you can and randomize what you cannot. Exactly. So if somebody comes and says time is a factor, you need to ask yourself, time is a factor, okay? Then I have two strategies. One is try to keep the time constant, which is the controlling strategy. Okay. The other opportunity is to block for time. Because you might come and tell me saying, I don't want to keep the time constant because what do I keep it constant to? Should I keep it to 8? Because if I keep it time constant to 8 a.m., I might be, incorrectly advantaging dosais. Because people who wake up early tend to like dosais more than people who wake up late. The problem with controlling is what do you control to? What you control to might bias your experiment. Some things the controlling is not a bad thing because it might have no relationship with the factor of interest. But in other cases, controlling can be a bad thing. So what you might choose to do is block. You might choose to say, okay, on 4 of these Wednesdays, I'm going to give breakfast at 8. On 4 of these Wednesdays, I'm going to give it at 9. Okay? Great, a block. Now let us say there's another factor that you didn't even think about. You try to randomize. As long as you're randomizing enough things, other things that are happening, it still might go one way, but at least you did not systematically induce the bias in the problem. Okay? Yeah. Mm-hmm. Mm-hmm. Okay. We'll move away from breakfast items. I'll take another example and let's see if the controlling, blocking, and randomizing kind of fit it. Huh? Okay. So between blocking and randomizing, right? Okay. Let me think about a good one. Okay. So let us say you wanted to look between, you wanted to do some kind of studies associated with promotions. Okay. And you own some brand. Let's say your t-shirt, your shirt brand, whatever, Levi's. Okay. So Levi's has some 200 stores out here. And so what you're going to do is on half the stores, you want to give 5% discount. On you want to see, okay, on half of them, you're going to give a 50% discount. On the other half, you're going to say buy one, get one free. This is actually a very commonly done thing. Marketeers try to understand whether buy one, get one free is as good as 50% discount. Okay. So what would the blocking approach be? Suppose we find out that the stores themselves are categorized as, I'm thinking of, how will you differentiate stores? Area, no? So maybe in the heart of the city or outside. So what is a one word I can use for in the heart of the city? Urban, suburban. Okay. All stores are classified as urban versus suburban. Okay. Controlling approach would have said, look, urban, suburban makes a big difference in terms of sales. Urban, suburban has no influence on whether you get buy one, get one free or this thing. So just pick one. Go do your experiment in that one thing. Pick all urban stores. Within urban stores, half of them buy one, get one free. Half of them 50% discount. Controlling is clear? Okay. Yeah. Blocking guy comes and says, no, 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 no. Don't do this. Because I suspect that one of your alternatives will be, I suspect that this idea of buy one, get one free is very popular in urban stores, but not as popular in suburban stores. My job is still across all stores, figure out what is the right thing. So, however, urban versus suburban sales are very different. So blocking will say, take all the urban stores, split them into two. Half of them buy one, get one free. Half of them 50% discount. Go to all the suburban stores. Or I'll make it even more interesting. I can only experiment on 100 stores. In controlling, I would have taken all 100 from urban or suburban. 50 buy one get one free, 50 to 50% discount. Okay. In blocking, what do I do? That 100 I'll split into two. 50 urban stores, 50 suburban stores. Within the 50 urban stores, 25 of them to buy one get one free, 25 to 50% discount. Within the 50 suburban stores, 25 to buy one get one free, 25 to suburban. So you see how controlling went and made it 50-50 all in urban or all in suburban, because you were controlling. Blocking made you perfectly split the buy one get one free and 50% discount within urban and within suburban. Randomization, if it is an alternate approach, would have just said, man, just take these 100 stores randomly and take a random 50 and assign it to. So take all the stores and just randomly allocate it. Why is that a good strategy? Well, that's a good strategy if, for instance, your brain had told you that urban-suburban divide existed. See, at least now you are able to say urban-suburban. Have you thought about stores that are on the main roads versus in a lane? Have you thought about stores that are big versus small? There can be so many other factors you've not thought of. What is your best hedge? What is your best protection against the things that you didn't think of? At least now I'm going to go toss a coin and call it urban or suburban. I mean, buy one, get one free or 50% discount. In fact, many times these happen together. Imagine I did the blocking. Now that I've done the blocking, that means for 25 stores out of the 50 urban stores, I'm going to do buy one, get one free. Which 25 of the 50? First of all, which 50 of the urban should be randomly picked? Imagine there are 200 urban stores. You randomly pick a 50. Within that 50, you randomly pick a 25. And then allocate the buy one, get one free. That way, if there's something systematic going on also, you can kind of wash your hands off of that and say, it's not my fault. You know, I've at least randomly allocated. There won't be any systematic biases. Randomizing, blocking, and controlling a little clear?
Yes, sir. Thank you, sir.
Yeah. So the question is, if you consider randomizing, probability will come to picture. So what happens when you do randomizing is you don't protect yourself perfectly, because there is a random chance that when you allocated buy one, get one free, about more went to urban and fewer went to suburban, right? But this is where, I don't know if this is a concept that's been taught to you yet. There's something called bias variance dichotomy that you would have studied. Some of you are saying yes, some of you are saying no. You're making the bias zero. Because now I'm randomly allocating, there is no systematic bias. The expected value for buy one, get one free is equal to the expected value for 50% discount. I'm not saying those two will be equal, because by chance, one would have gotten more urban or more rural, more suburban, and the other would have. But the expected value is equal for the simple reason that you randomly allocated. No, what we're doing is we're taking care of systematic bias, right? We can't make variance zero, but we're getting rid of bias.
Noise here is the bias.
Sorry?
Noise.
No, the
word-
noise here could be that it's a variable that went, so the noise variable here is the suburban versus urban, right? It's a noise variable because it's not a variable we can control. I can control the amount of promotion I give. But the noise variable is suburban versus urban. The noise variable in the ice cream case would have been the temperature. So when I say what about noise, I'm referring to the fact that there are variables in the environment I can't control, but which do influence my output. So there are input variables and then there are these noise variables. And here suburban and urban are a example of. Yeah. Yes. So because you don't know how many, that's an excellent question, because you don't know how many noise variables that are there, right? This randomization is like one catch-all to say, I'm hopefully getting rid of all my problems by doing this. Which is why that mantra is block what you can, randomize what you cannot, right? But in doing that, they have missed out poor controlling. But blocking and controlling are definitive strategies where if you know the variable that you think is an unnecessary noise variable, you can systematically remove its effect. Controlling and blocking systematically removes the effect because exactly 50 suburban stores have given this to and 50 urban stores have done this too. You know, there's a very precise approach to blocking and controlling. However, randomizing is to kind of wash our hands off and say there are hundreds of things I've not thought about. At least now the expected values are equal, right? So again, I think famous examples used to come from agriculture back in the day. Back in the day, when, by the way, many of the things that I'm saying were 40s, 30s, like way back when statistics was coming up, right? So we are applying them here, but back then in agriculture, people used to say things like blocking and controlling for things like sunlight, water. But you might not have thought about many other features, such as is it in the edge or is it in the center, the crop. So wind effects you've not probably thought of. So as long as you do random allocation, you're protected, right? Okay. Yep. Yes, absolutely. So controlling and blocking usually come up with the help of your knowledge of the system, not dictated by data science, but dictated by fundamental principles, right? And then you use randomizing as a way of protecting against everything else. Okay, so in the interest of time, I'm just going to move ahead very quickly. So one of the approaches, one of the most common approaches is to use designed experiments. And what does a designed experiment actually mean? It means that many times we're going to use matrices, okay? And many times we're going to try and simplify a matrix to just two values. So let us say one of the values was like promotions, the other was discounts. -1 meant no promotion, +1 meant promotion was given, was made. -1 means no discount, +1 means discount. So in the first case, what did you do? You did nothing. In the second one, what did you do? You gave a discount, but you did not advertise it. The third one, what did you do? You ran an advertisement, but gave no discount. The last one, you did both. This is a balanced X matrix. This is your X matrix, this is your Y vector. This is a balanced X matrix. In the normal life, if all you had was observational data, what would you have seen?
Some row might be missing.
Which rows specifically in normal life for promotions and discounts, which rows do you think would have been primarily present and which rows do you think would have been very rare to find?
Middle to one.
Typically, you'll see the first row and the last row, right? In some cases, they won't do anything, right? In some cases, they'll give the promotion and shout about they'll give a discount and keep shouting about the discount, right? At the very least, you'll rarely find a row where a discount is given, but a promotion is not made. You'll rarely find this -1, 1. And when this is missing, again, we're going to see how it does not help you do any regression analysis and learn anything useful. Okay, but the approach that we've taken is one of using two levels. Now, many quantitative variables, suppose one of these variables had to be temperature also, we're going to convert it to low temperature and high temperature. So we're going to binarize all our input variables and we're going to do it as minus ones and plus ones. So if there are two variables, you'll have four rows. Now, sometimes when you have three variables, and in this case, if my first variable has three levels, not just minus one and plus one, but minus one, 0, plus 1. How many rows will I have? The first one has 3 levels. The second one has 2 levels. Third one has 2 levels. So don't count the rows, but try to 12, right? Like, so it's 3 multiplied by 2 multiplied by 2. So that's the common thread that you'll see. Also, sometimes for a given combination, you don't have to just get one value. You can get multiple values. You can average it and put it here, or you can just repeat the matrix multiple times. I have, for simplicity, just drawn it as one matrix. But the beauty of this matrix is, what is the correlation between the columns? Between A and B, what's the correlation? Be able to kind of look at it.
Orthogonal?
They're orthogonal, which also means that their correlation is 0. They're uncorrelated. When this stays constant, this is right? And so when this stays constant, when this goes up, this is gone. So every combination is actually happening. There's no trend between these two. Now, you can extend it to 3 factors and 4 factors. What's the common thread? Uncorrelated. But the number of rows, how do you get it quickly? It is always 2 to the power. So it's always the number of levels to the power of number of factors. Number of levels to the power of number of factors. And have you found any pattern of how to quickly get the whole matrix drawn? Start with either the left-handmost side and break it into 2, and then break the next into within that, and within that till you get to alternates in the end. Yeah. But this, in the sense of ANDs and OR gates, right? That's not what we are doing here. You can look at analogies between truth tables and some of what we're doing here. But again, that's not our goal out here. Okay. So now what I'm going to do is I'm going to help you analyze data. Okay. I've shown you how to construct the matrix. After you construct the matrix that you saw in the previous slide, what are we going to do? We're going to go get Y values for this. So for each row, see, this is a row, right? So for each row, you've got a Y value now, or a set of Y values for each row. You can take the set and take the average of it. You can put one Y value. So for each row, you have a Y value, as opposed to the previous case where only for some rows you were having lots of Y values. Now you have a very nice balanced design, right? Now, how do you analyze this data? The good news is you can run a regression on this data. Just 1 second, and I'll take your questions in a second. So I can put a Y, I can give you some data, and I can just downright do a regression, and I'll get beautiful results. But I don't even need to do that. My life is, what I'm going to explain in a minute is that I'm going to do the equivalent of a regression, but regressions have become even more simpler for me now. Why? Because each variable has only 2 levels. If I were to logically look at the relationship between Y and each of these variables, how will I do it? You just plot it against each variable. So here is a simple exercise called a marginal means plot. But before I go there was a question. Oh, what are the three factors? It could be anything. Suppose we take the example of promotion, discount, and you can add a third this thing. In the case of suburban would be one row. I mean one column, sorry. So location would be one, discount type would be the other, and maybe size of the store would be a third, right? Take anything that you love, any domain that you like. Only thing that you need to do for an experiment is you need to make sure that every combination is equally represented and that it's only got two levels, right? There are experiments for more levels, but 90% of what you'll see, because how many data points do you need to draw a straight line? 2. So as long as on the x-axis I'm able to point to two things, all linear effects I can capture between the variable and the output. Okay, so now I've done this. Okay, what I'm going to do is I'm going to take any one variable, C. I'm going to look at the average y when C was minus 1, average y when C was plus 1. Okay, and I'm going to plot it and I'm going to say this is the effect that C has on y. Why is this fair? Why is this okay? And of course, you could never do this on observational data, because who knows if when C was at minus 1, more B's were at minus 1? Who knows when C was at plus 1 if more B's were at plus 1? In this example, if I completely make some rows disappear and then say A at minus 1 and A at plus 1, that's not fair, because you've only seen A at minus 1 when B was at minus 1. You've never seen A at minus 1 when B was plus 1. How do I know if it's the effect of A or B? But when I do this with C, what am I getting? Let us say I did C at minus 1. When C at minus 1, that means I'm going to take the average. My height is a serious problem here. So I'm going to take C at minus 1, which means this value, this value, this value, this value, and take the average of all of that. Okay? And similarly, I'm going to take the average of this, 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 and then I'm going to plot it, right? Now, why is this fair? Why is this a reasonable way of doing things? Can you tell me a little bit about the values that A and B take when C is minus 1? When C is at minus 1, every combination of A and B is represented precisely in time. That's the beauty of this matrix. So yes, you are measuring data of C while A and B are set to other values, but they're perfectly set to other values in a balanced way. So even if A and B have an influence on Y, which they are very likely to, that effect is cancelled out in some sense, because you've got, so when you can say, hey, when C is at minus 1, A and B were at minus 1, but you will find a C at plus 1 for which A and B will again be minus 1. Which one is that? Second one. Right? So let A influence Y. Let B influence Y. Let A and B together influence Y. Let A mix with C to influence Y. I don't care. It is still fair for me to plot C at minus 1 and plot C at plus 1 and get the net effect of C on Y, which is exactly the coefficient that you will get if you run a regression with C in there when you do a regression. You will get exactly half the slope of this, because it's minus 1 to plus 1. It's not 0 to 1. So a regression will give you these results, but the beauty of such an approach is you can just blindly say that the effect of C is nothing but average of Y at C is equal to minus 1, average of Y when C is equal to plus 1. You cannot do that on observational data when you're doing a linear regression. The coefficient you get is not the coefficient of on average minus 1 and plus 1. Okay? Now, you can do the same thing for many different things, but this takes you kind of running low on time. But so this allows you to do another fascinating thing also. This allows you to study something called an interaction. Okay. So an interaction is something where one variable has an effect. So multicollinearity is this problem where two variables are correlated. I've gotten rid of that problem. Okay? But is it possible that one variable can have an influence on the influence that another variable has on the output? In other words, imagine something called promotions. Are promotions in general good? Maybe not. Maybe promotions are effective only when there is a discount. Maybe. I don't know. But look at the sentence I used. I said promotions are not good in themselves. Promotions can be bad, right? Why can a promotion be bad? Because they cost money. If it doesn't commensurately increase my sales, a promotion is actually a loss, right? So a promotion, you could argue, could be such that the promotion's influence on the output, which is called net profitability, is in itself influenced by whether you're giving a discount or not. So many times we're dealing with systems where the inputs are not correlated. That's multicollinearity. But there are interactions between the input variables, which means the effect that variable A has on Y is influenced by what variable B was set to. We kind of saw this with the dosa puri story, didn't we? In a sense, it's not like dosas are by themselves good or puris by themselves. It's the fact that on certain days, something was good. So we could be dealing with systems like that. So what we want to learn is whether there is an interaction between two input variables. A simple way to do that is do the same thing, C8 minus 1 and C8 plus 1. Okay? But have a separate one for B8 minus 1 and B8 plus 1. So you've got two lines, right? So what does the blue line tell you? That means you've taken all the times when B was minus 1 and then looked at all the C's at minus 1. So let's take that blue line, and how would you have calculated that here? So first of all, you would have taken all these points only. And within this, you would have taken all the cases where C was minus 1. That means you would have averaged these two and gotten C at minus 1, averaged the plus 1s and gotten C at plus 1. So now, can you tell me how this graph should look like under different situations? I'm going to start plotting the situation. If C has no effect on Y, what would I see? No intersection and parallel. That is, if C has no effect on Y. I just want, C has no effect on Y. B, let us say B has some effect on Y. C has no effect on Y. And C and B have nothing to do with each other. It will be a horizontal line, right? Right? Now B has some effect on Y. So how will that look? Yes, B has an influence, but C has no influence. B has an influence on Y, C has no influence on Y. Look. I just pause for a second and think, and I know you guys got this answer. C has no influence on Y. B has an influence on Y. Positive or negative, I don't care. And C and D have no interaction effect. parallel, but they're both going to be horizontal, right? You're going to see two horizontal lines. The first line is horizontal because C has no influence on Y. The second line is also horizontal because C still has no influence on Y. But they're parallel to each other because B has some influence on Y, and that influence is what is captured in the height difference between B at -1 and B at +1. Fair enough? Okay. Now, if C has an influence on Y, but B has no influence on Y, what should we see? We're not saying it has complete influence, we're saying it has some influence, right? C has some influence on Y.
C will be inclined.
Yeah, so it will be an inclined line. So it will be like that, right? C has some influence on Y. But what will B has no influence on Y?
B will be horizontal.
It will be one on top of the other. They'll overlap, right? There'll be two lines one on top of the other. Now, obviously we've seen, you can see other combinations of it, right? If C has an influence on Y and B has an influence on Y, but they have no interaction with each other, you're going to see two lines like this. Correct? C has some influence on Y, B has some influence on Y, but they're still going to be parallel because there is no interaction. Now, what does it mean to say that C has no influence on Y, B has no influence on Y, but they have a strong interaction? It still has to be a line, no? There are ultimately 4 dots that we have to somewhere draw, and you have to connect the lines. I'm going to come to your answer, but first let's just confirm. If C has no influence on Y and B has no influence on Y, what should you expect? Two overlapping horizontal lines, right? C has no influence on Y, B has no influence on Y. So there was an answer on intersection. You want to give it a shot? No? You change your mind? Alright, I'm going to try and draw a line for you and you tell me what you think about it. Because, I mean, in all honesty, this is a hard question for someone who's listening to it for the first time. I'm going to draw with my fingers, okay? My long fingers. Think of two lines like this, okay? Like a perfect cross, and try to make it symmetric such that when you do the cross, the average of this point and this point on this side of the cross is equal to the average of this point and this point on this side. Which means if I were drawing a marginal means on C, it would have had no effect. Okay? The average height of this line is equal to the average height of this line, which means if I were to draw a marginal means on B, you can't say one line is above the other line. When B had an effect, one line was above the other line, no? Now one line is not above the other line. Now one side is not above the other side. But at the same time, are they both not parallel on top of each other? No. What does this mean? This means that C has an effect on Y that is this way when B is -1. C has the opposite effect on Y when B is switched. C by itself has no effect on Y. Because on average when C is -1, Y is the same as when on C is +1. Similarly, B has no effect on Y because average when B is -1, Y is the same as when average. But it's not because C and B work together to influence? Why? One of the favorite examples that I kind of like to give is similar to this promotion thing. Okay, so imagine you run a pizza shop. Okay, in this pizza shop, you have to on a daily basis, you have to hire labor for doing delivery. In the beginning of the day, you need to commit to the number of people to hire. So you can hire 3 people or you can hire 10 people. Beginning of the day. If nobody comes, pizza place is swatting flies, you have to still pay those 10 people. Okay. Similarly, at the beginning of the day, you have to decide whether to print flyers and distribute it or not. Promotion, personal recruitment. 2 factors. You can either not print the flyers, -1, or print the flyers, +1. You can either recruit only 3 people, delivery boys, or recruit 10 people, +1. This is just an example I've made up. Okay? Pizza shop is profitable when you don't print the flyers and you hire only 3 people. The people who are regular customers call, these 3 people go. You run a good profit. Why? Because your costs are low. You've hired only 3 people. You've printed no flyers. Now imagine you go and only print the flyers. Your expenses have gone up. More orders are coming in, but how many pizza boys do you have? Only 3. You're not able to translate that to profit or sales. As a result, your profits, you get a loss. So when you increase promotion, you increased, promotion, but kept recruitment low, loss. Similarly, do the opposite. No promotions, but you hire 10 people. You have to pay them salaries. But are you getting more phone calls? No, right? Again, loss. Now, what happens when you increase promotions and recruit more people? Profit through the roof, right? Now, lots of people are calling and you're able to monetize that. A perfect case of this. Can I say recruitment in general is good? No, recruitment is good only if you promote your product. Similarly, can I say promotion in general is good? No, promotion is good only if you recruit more people. That same variable called promotion can go up if recruitment is high. The same variable called promotion can go down if recruitment is low. So this is the concept of interactions, and you can get that by observing closely this graph. In the interest of time, I won't spend too much more time on experiments. I'll just talk a little bit about active learning. So I've got another 15 minutes. I'll talk about for 10 minutes on this concept called active learning, and then I'll talk a little bit about online experiments and wrap up. Okay? We've spoken a lot about conducting experiments, which means picking these matrices for which we need Y values, right? Now, what if you can be sequential or adaptive, right? One way of thinking of sequential and adaptive, again, is the old experimental framework where you do something, you get the results, and then you come back. So you don't create the matrix upfront, but you have to do things almost at one at a time. So imagine if you're like crash testing cars. First of all, you don't want to randomly take a set of cars that have crashed and analyze the dead bodies, right? That it's not ethical, it's problematic. And I said it in the most morbid way, but what you do want to do is look at dummies, crash test dummies, and see the kind of impact that they've taken up. Now, a design of experiments first would say, hey, we need to, let us say some of the factors were the speed of the car, the speed of the collider, side or front impact, right? With or without airbags. Some 3 factors, right? The experimental design person would have quickly said 2 to the power 3, 8 combinations, 8 cars. They might have even said we need multiple data points on each, 8 times 3 or 8 times 4, 32 cars we need to. Sometimes you don't have that kind of budget, right? Each car costs a lot of money. Also, what if after 2 or 3 crashes, it becomes really obvious that speed makes a big difference, right? Suppose you say that, hey, car's going fast, means definitely the dummy is going to brake, or car's going slow, definitely the dummy is not going to brake. You don't want to spend as many resources testing something that might be obvious or useless. You want to move on to other variables. It's almost like a game where you're trying to find the points in the input space that are giving you the most information. The design of experiment strategy is to look at that input space and put points in a very balanced way. Realizing that if some points are not there in some regions, it causes a big problem. However, once you start fitting a model, you might realize that some regions are more important than other regions. I need to put even more points there, right? So in the case of crash testing, I might want to, after a few crashes, build a model, run a regression, run a k nearest neighbors, run a linear discriminant analysis, then see at which points is my prediction error the weakest. I might want more points in those locations. So as opposed to the one-shot approach that experiments take, which is even before looking at y values, I carefully curate the X matrix and then say, oh, I've made sure there are points in a very balanced way. Now go give me all the y values. That's the experimental design strategy. What does active learning do? It says, hey, build a model with the points you have, and let us use the model to tell me where I need new points. So you have to think of active learning as a loop. Model tells you which point, and as soon as you give it a point, you get a y value. You redo the analysis. Once you redo the analysis, you realize which points are the weakest. So you're going in a loop. And you have to see that the biggest benefit of active learning is that your accuracy goes up more steep. I don't have a graph for this, but what you should expect. It's some drawing tool. Okay, again, hands will have to do, so we'll do the best we can with hands. Okay, so y-axis is accuracy of the model. Okay, let us say you have a model with some level of accuracy, and the x-axis is the amount of data that you have. Okay, and let us say you're analyzing crash test dummies or something, right? Now, what do you think this graph is going to look like? Accuracy for classification. For regression, what would you use? I want to test you on your basics of this. Mean squared error. Good if all of you who remember MSc. So for regression, you'd use MSc. For classification, you'd use maybe something like accuracy or F1 or ROC curve, some measure. Okay? So you've got this graph, data, accuracy. What do you think this graph is going to look like? 45 degrees? Really? That means it's going to go into space? It can't go above 1, right? Yeah, after a certain level. So usually the learning is the steepest in the beginning. It goes up very steeply because with more points, each point is more valuable. You're learning something and then it will plateau out. But that is under the assumption that the data that you're getting is random. Active learning asks the question saying, if I can pick the data for you, can I get my learning to be even more steep? Can I reach the same 90% without going so far on the x-axis, right? So that I have learned more with lesser point. Why? Because I didn't give you useless points. You might have some 200 points already in certain regions of the space, and that's not helping you learn much better. And so there are many strategies in active learning, ranging from uncertainty sampling, which says, go give me points where I'm most uncertain about. Or give me points which is going to maximize my information gain. There are lots of mathematical criteria, and we won't go into each of these. But what you're essentially doing is you're exploring the value of the data after exploring the fit-in model, right? So after you get a model, as opposed to design of experiments, which is even before I do my first regression, I'm going to tell you which X matrix I want. This says, go do the regression, tell me how successful you are, come back to me and tell me which new data point you want. Advantage is that you can get more with less data. What's the disadvantage? It's telling you which points, which is what experimental design also does, right? It does so saying -1, +1. Problem is, this is sequential. Experimental design will say you need these 20 points. I can parallelly collect 20 points. In one shot, I can send 20 people out to go collect 20 points. Here I have to collect 1 point, go fit it into the model. Imagine being able to go to 30 stores and say you run promotion A. Go to 30 other stores and say, run promotion B. Here you have to take one store, run the promotion, see what happens, and then go to the next store to decide what to do. Works really well when you want to conserve the units like crashing a car. Works really bad if you've got 200 stores sitting there swatting flies waiting for you to learn from them, right? Clearly there are advantages in some domains. You need a one-shot parallel approach. In some domains, you're happy with the sequential approach. If I'm an online ads kind of a guy, I can be fully sequential. I don't have to give a promotion, wait for time, collect the data. It's not like a physical shop. I pop up an ad, I'll see whether a guy clicks on it or not. I've immediately got my feedback digitally, right? I can move on to the next, this thing. So active learning is a topic in machine learning where the AI agent, right? So not only do you analyze the data, you control which data, picks the point. That is a point in the input space for which it receives the output. Typically, the output is said to come from the words that you might hear if you Google this is an oracle or a user or an environment, right? So these are the words. Basically, from the environment, you get the feedback and you get what is called a label. The point selected can be one point in the input space or it can come from a set. If I say 30 points, I can tell you which point is the best point from that to give me this thing. In other words, sometimes I can come and say, hey, make the car go this fast and go impact it from this side. And that's like literally curating a point. Other times I have to pick among 20 cars to go crash. There I have a set of inputs from which I need to select one. Okay? I just thought I'd also show you some cool graphs that I saw online. So here is one and I've given you the reference, so I'm not copying it, someone else did this. But here's a clear case where if you just randomly pick greens, so clearly the decision boundary is this. Okay? But if you just randomly pick points, there is a good chance that you'll get something slightly off, right? Because I'm not giving you this much data, I'm giving you some small amount of data. At the same time, you let an active learning agent pick. It will probably try to pick points that it thinks are the most relevant because one active learning strategy is to pick points near the decision boundary in classification. You're getting a much better line, right? A more dynamic version of this you can see is as data points kind of are given, how the accuracy changes. You get another data point, you get another data point, you kind of keep learning. Now imagine if instead of getting you the data point out here, I instead picked a data point out here, it's not going to influence the line too much. I mean, we are all cheating because somewhere we know that the dashed line is the correct line. In the real world, you won't even know that. But at least you can start telling which points, getting reds and greens. What I can't control is whether the color that will show up is red or blue. But I can control where you give me the feedback from. Okay? Okay. So this is with respect to active learning. I just want to take 2 minutes to talk to you about one other.
Sir, before we move ahead, I have one question. Sir, means with this active learning, we can reduce the number of the experiments which will be conducted.
Yep.
And with the PCA, we can reduce the number of features which will be required for the. I'm mixing PCA.
No. I'll answer this question. Let me finish this in a minute,
sure.
and then come back to the question, because when PC, okay, so for most of you have taken a class on PCAs, right? So with PCA, what you're getting is you're getting new features. But even if you use one of the principal components, that one principal component is a combination of all your original features. So when someone kind of says with PCA I'm reducing features, I just want to make sure you're not reducing any number of features in the original space. If you have 5 variables, I will go into a tangent into PCA. That's why I'm saying, we'll come back to this question, okay? I'll just quickly talk about online learning because it's kind of related to this, and then I'll come back. Okay. So what is the online and live setup? So far, everything we've talked about requires you to pick a point and get a label, right? Which helps you build a model, which is perfectly fine if picking a point means doing something. So let's think about what picking a point means. Picking a point, for instance, in the promotion side, picking a store and going and giving a particular type of promotion and a particular type of discount, correct? You had to do that, and then you saw the consequences of that. What is the other examples that we've spoken about? Crash testing cars, right? So let's stick with the crash testing of cars. So crash testing of cars in the active learning side, we said, hey, you got to move this car this fast, and then you have to do a front impact, and then you get an output Y. And what did the output Y look like? The dummy survived or not, right? Now, what would you have called as a bad experiment? In the offline setup, what is a good point or a bad point? Excellent. A good point is something that gives you new information, right? One where it tells you something. So obviously a bad point to test is, imagine if I really know that a car that goes slow, that does a front impact, does not crash. If I go do that experiment again, that's a bad point, because sure, the outcome is that the dummy didn't die, but it doesn't help me learn anything. My model's accuracy is not going up, right? However, there are certain settings where the experiments that you run are not sacrificed towards learning. You're messing with the live system. I'll give you an example. Imagine if the experiment itself was a little bit like the promotions example. There, if I go give a promotion or not, I am in the real world chasing away customers. So sure, for the sake of an experiment, you can say, go give promotions or give discounts, or don't give promotions, don't give discounts. But is it fair to say that in that experiment, a good thing is only a thing that helped me learn? Isn't a good thing also one that made me profit? That's not the case in the crash test. In the crash test, if the dummy survived, it's not a good thing if it did not help me learn. Because my goal was not to preserve this car. The car is anyway going to be tossed away. But many times we experiment on the live system. We don't experiment offline. The things that we experiment on aren't going for scrap. There, we need to balance exploration and exploitation. So in an online thing, let's say an online ad, or this promotion or discount thing, or some budget spending, not only do you care that the thing that you're messing with helps you learn so that you make profit in the future, but the thing you're messing with is itself giving you profit and loss. Now that matters. I'll give you an example to tell you why it matters. Let's say you're given, what is that number? 1 crore, right? To improve about 200 parks. This example, by the way, is comes from a real world consulting that I did with the government. So the numbers are not exact, but you're given a budget to improve about 200 parks. Okay? That comes up to what, 50,000 rupees per park? Okay. You can either build slides or swings in the park. You have no idea which one is better. Right? So what do? You decide to experiment. So now, if you take a designed experiment or an active learning framework, what people might have you do is, first of all, if you randomly pick one and you don't experiment, who knows? Maybe slides are good, maybe swings are bad. You're flipping a coin, you don't know what you're going to get. Let us say you pick one park, build a slide, one park, you build a swing. You see which one is good. What's the problem with that approach? I can't hear you. First of all, the other parks are sitting around idle. But the second problem is also, even if you're okay with just one phase of waiting, the problem is, who knows, maybe this one park got lucky. There's no statistical significance, right? We need to experiment more to know what is right. Okay, so all of this supports more active learning. Active learning is sequential, it's a problem. More designed experiments, right? Try every combination. On large parks, on small parks, build slides, on this thing. So use more parks. But there's a problem. Once you go and use the budget to build one thing, you've lost the money. You can't go and pull the slide out. So while a statistician who studies design of experiments might come in and say, you know, to get statistical significance, you need to invest about 75 parks or 80 parks, build slides, 80 parks, build swings, and let's see what happens. Great. At the end of it, you've got statistical significance. You know that slides are better than swings. Okay? But what happens after that? Sure. How many parks do you have left over? You're left over with just 40 parks, right? Whatever you found, sure, you can go implement it, but you've already wasted 80 parks with the suboptimal treatment. This is what we call the exploration versus exploitation dilemma. All of online learning says we need a modified objective function that looks at something like cumulative benefit or cumulative regret, right? And there's a big area called the multi-arm bandits or bandits in reinforcement learning that looks at this at the sequential level. I gave you an example that's just in a parallel deployment, but the long and short of it is, design of experiments and active learning is offline learning. There's a whole different topic, which we won't get into, but I just wanted to motivate it for you, called online learning. And in online learning particularly, this is a parallel example, but in sequential learning, you're balancing two things. You're balancing the need to learn. Like in active learning, you want to learn. By messing with the system, by playing with the system, you want to learn what's good, because that's going to help you make profits tomorrow and give good, but at the same time, while you're messing with that, you're also driving away customers. You're also giving suboptimal promotions. So when Google decides to put ads, it's thinking about this exploration versus exploitation dilemma, which says that I need to try some new ads to know whether they're successful or not, because for the ads that I don't try, I never have the data. So I need to experiment. But at the same time, I'm not going to experiment blindly because it hurts my customers. It's driving customers when I show bad product, right? Okay, I'll wrap up with that. Let me answer the question on PCAs very quickly. So PCAs as an approach, right? If you say I have come in with 30 features, how many principal components can I construct from that? I come to you with 30 input variables. Okay? So you've learned some formula to construct the first principal component. Can you construct the second principal component? You can construct the second principal component. Can you construct the third principal component? Guys, you've done one class on PC. I mean, have you done one sessions on PCAs? No. Some of you have, some of you have not. Okay. Okay. It's not the same thing as degrees of freedom, but core concept is, so again, only for those, I'll keep this brief, only for those who know what principal components are. Principal components are basic when you have like some number of input variables. You can take some weighted average linear combination of these inputs to create new variables. How many such new variables can you create? 30. You can create as many numbers as the original features. Now, why is this an advantage? It's because the first few features you create capture most of the information, and you can almost certainly ignore the last many. So in a sense, it's like taking a problem where there were 30 input variables, and some of these variables could have been highly correlated and have multicollinearity, to down to 3 or 4 orthogonal variables. But while this looks good from a statistical perspective and problem solving, each one of these 4 or 5 is itself a weighted average combination of all of these 30s. So you're not eliminating any original features in its entirety. So if the goal is sometimes, out of these 30, I want to throw 20 away, principal components is not the way to go. There are other techniques, for instance, like lasso regression, which you might have come across, which allow you to completely eliminate input variables. Right? So anyway, that was a little bit of an aside, but I just wanted to wrap up with this online learning as an example. Any other questions, comments? Yep. Yeah, so it's a good question. So you're saying, look, you've built a model and you're getting a good accuracy. However, over time, that is not holding up. First of all, to know that after some time it's not holding up, you'll have to have a notion of test data. Typically, what is done is to see how the sample of the test data is differing from the training data on which the original model is trained on. So again, there, active learning could help, right? Because it might help you identify the regions of the input space which are very sparse. So I would say, yes, you could use active learning where the goal is to quickly come up to speed with as little data as possible. But if that is not the goal, if the goal is not, hey, save the data points for me, then I would only blindly see how this test data is differing from my training data and do whatever is needed to adjust for that, right? Active learning only helps you insofar as saying, I don't have the budget for large number of data points. I want to get as much accuracy with as few data points as possible. Then definitely you can use active learning in this context, as you say, to, with the fewest new data points, bring your old model back to up to speed in the new setting. However, if you have no constraint on the number of data points, the only thing you need to do is to try and understand how is the new test data differing from the training data that you learned, and try to see in which regions you have to modify the data source, right? So a thing that might be more relevant here might be something called meta learning as well, which is how do you learn from previous model, how do you put models together to you know, come up with conclusions. Kind of answers your question.
Sir, I have one another question. Sir, your class has given me a deeper insight that just don't look at the data, and when you look at your X matrix, then go and look at the how much controlling is there, how much blocking is there, and how much randomization is there to understand one level ahead. But sir, in the practical scenario, when I was working for an R&D company, then there was possibility, and we were designing that experiment. We were how many experiments we have to do to arrive at the conclusion. But when I was shifted to the business scenario, so there are not possibilities just because of the profitability. We cannot design the number of experiments. The changes are not possible. So in the business scenario, how we have to take the insight from the data, because there is a lot of constraints are there. We cannot change the parameters much.
Yeah. So what I talk about only talks about how you design the experiments, right? If you choose to look at the X matrix that is given to you, if you are not curating the X matrix, but if you're only going to analyze the X matrix, those set of techniques are different, right? Like for instance, you would have learned something called variance inflation factor. It's an analysis of the X matrix to see how good or how bad it is. So in situations like that, you can do that. You can analyze the X matrix and see, hey, it's working, it's not working, and so on. What this helps you do is if you have to create the X matrix, how do you create it? But if you want to analyze the X matrix for goodness, of how good is the X matrix for me to go ahead with analysis, variance inflation factor, or any of those things that you would have learned in regression diagnostics, multicollinearity, VIF, heteroscedasticity, all of those could apply, right? And ultimately, with more and more machine learning, you're getting to one bottom line called cross-validation, right? Cross-validation error gives you a good indicator of how, if you hide data, whether you're overfitting or not, and things like that.
Thank you so much, sir.
All right, last question, and then we'll wrap up. Too many people are running away. Yeah. Say that one more time. Yeah. So good point. So you're saying exploration versus exploitation arises due to lack of data. And so can you just kind of simulate the environment? So essentially, the problem arises, yes, in a way because of lack of data, but lack of data arises because you can't go offline, because you're dealing with a live system. Doing a simulation is again an escape route, right? It's a way of going offline. In a simulation, if I go and run horrible scenarios, no problem. In a simulation, again, a waste of time and waste of computational resources is points that don't help me learn, not points that are giving me a bad why. Right? The second you say simulation, you're going offline, which is a strategy. Lots of times people want to go offline. Why? Because if you're offline, you can really mess with the system, play with the system, and see how it reacts. Right? But if it's a live, living, breathing system, you can't really whack it around to learn how it will react, right? So yes, people do look at simulations, and the reason people do that is to take it offline. But there are things that you just cannot take offline, right? Many times in social sciences, for instance, that's what the Duflos and Banerjee show. You can't imagine what it would be like if I gave a subsidy on a particular crop to someone. You have to go to some villages and go and do it and see what happens, right? You can maybe build a traffic signal simulator to see what happens if I change a signal strategy. But does that capture everything? Sometimes you have to go there and do it. In those situations, you have to be cognizant that you're dealing with a problem of exploration versus exploitation. Sure, you need to mess with the system so that you save more lives tomorrow. But by messing with the system today, are you killing more people? Right? That balance needs to be there. So in all of these cases, people create an objective function called total people that have died as a result, which would be high if you don't do any exploration also, because then you're running a random policy, which could as a signal also wind up creating more crashes. Then you say, okay, then let me try a 30-second timer, 60-second timer. You start playing with the signals. But as a result of playing, you're killing some people. So how many lives can I minimize? So metrics such as cumulative regret, cumulative reward, some notion of overall, not just what is the best settings for today, but what settings should I set it to such that I do well today, but such that I also learn from the data that comes from it that will help me save more lives tomorrow, becomes the bad. Okay. All right, thanks a lot everyone.